We have defined correlation and covariance matrices. Now we want to know, because these matrices have quite a number of various applications. So we need to know the properties of these matrices in order to exploit these properties, sometimes to reduce computational costs, sometimes to improve the accuracy of the result of data processing or data mining and so on. So this video, we are interested in properties of these matrices. These matrices are quite often used in learning processes, in estimation, detection, and so on. So the first property of these matrices is that these matrices are non-negative definite. It means that if you have these matrices, let's say RXX or CXX, doesn't matter, if you multiply it by any matrix from this side, A Hermitian and A, you always get a real number, and this real number is always positive. So doesn't matter. You could apply it either for RXX and so on. In other words, if you write these, because this becomes a row matrix, this becomes let's say n by n and column. So this will become an scalar. So it could be complex number and so on. So if you write it, you will get this summation. So it means that for all AI's complex number and any arbitrary complex vector of size n, if you put it in this equation, the result is real number as non-negative. Doesn't matter either for a correlation matrix or for covariance matrix. And the proof is very easy, because what you could do is that you could define like the A Hermitian X is a linear combination of your random variable, because A Hermitian X is A1 conjugate X1 plus A2, because this A Hermitian becomes A1 conjugate, A2 conjugate, etc., AN conjugate. So this part is this one. And this X is a column vector, which is, let's say, X1, X2, Xn. Now, if you multiply this row vector by this one, you get the first one times this one, second one times second one, etc., and then you add them together, which is this expression. You can obviously write it this way. So you could write it as, let's say, X1, X2, Xn, and then write A1 conjugate, A2 conjugate, etc., and then AN conjugate. And you see that the dot product of these vectors is going to be same. Now, if you consider this expression, now I want to calculate, this is X, I want to calculate mean of absolute value of X. So if I consider X to the power of 2, which is basically is equal to X times X conjugate, because something multiplied by its conjugate, it becomes non-negative. So I could say that this is, first of all, real and non-negative, because whatever phase this has, it has a negative phase of equal amount. So the phase of this number is going to be 0. So you will get non-negative. And if you apply expected value on both sides of that, you get expected value of 0 is 0, so on. So this part is obvious. Now, the next part of the proof is that this X to the power of 2 is X times X conjugate. So this is a summation, okay? And this is another summation. So this X itself is equal to this guy, okay? So this X is equal to this guy. And this X conjugate, I use this one. I have to put a conjugate on top of this one. So if I put a conjugate on this one, this X transpose becomes X Hermitian, and this A conjugate becomes A. So the second part is equal to this one. So this part is equal to this one. Now, now I look at this part. I'm here. Because this A Hermitian is not random, and this expected value is a linear operator. So I could, this A Hermitian is multiplied by something which is random. This is a linear operator, this is a linear operator, and here I could change the order. So I could take this one outside of expectation. Remember that this expectation is nothing more than some integrals. And these integrals are linear, and I could put this one. So I could put this one outside of the expectation. Similarly, I could put this A outside of this expectation. So what I get, this expectation operator, this part is going to go here, and this bracket is going to go here. So this is what I get here. And now, interestingly, in this part, this guy is nothing more than Rxx. This is by the definition that we had in the previous video. So what we have proven is that not only this guy is non-negative, but also is real and non-negative, real non-negative, real non-negative, real non-negative. And also this is true for all values of A, any complex vector. The proof is similar for covariance matrix. So if our random variables are linearly independent, so what will happen to covariances? So if what was the definition? We say a set of random variables, we call them linearly independent if any linear combination of them, the mean of this guy is always non-zero. So we call them linearly independent if this value is 0 we call them linearly dependent if these could become 0 for some non-zero values of A. In other words, the energy. So remember that a mean of any random variable, let's say z to the power of 2, this is called, by definition, the energy. Sometimes we call energy, sometimes we call it power. I know that in physics, energy and power are two different entities, but when we deal with random variables, sometimes this relates to energy, sometimes it relates to power, but the truth is that you have to multiply it sometimes by a resistor to become energy, sometimes by something else to become, but this is the ambiguity can be removed when you deal with the physics of the problem. Here we don't, so this is why we use the ambiguous terms of the energy. So the power or energy of a linear combination, if we could make it 0, then we call it linearly dependent. That means that if they are linearly independent, that means that there is no linear combination with non-zero elements which could make the power 0. That means that they are in a space of n dimensions. So if they are linear independence, means that they are in a n-dimensional space. Remember that this is totally different with independence. Independence, when we talk independence, we talk about distributions, but here we only talk about, because this definition only requires the covariance matrix. So this definition can be simplified into this, because obviously this is equal to this quantity is equal to A Hermitian Rxx A. So if you could make these equal 0, then we call it linearly dependent. In other words, if the covariance matrix is singular, if it has an eigen value of 0, we call it linearly dependent. If Rxx has an eigenvalue equal to 0, then we call it linearly dependent. That means that one of the random variables is equal to a linear combination of the rest of them. Now, let's move on and see other properties of covariance matrix. The eigenvalues of these matrices are always non-negative. So if you have any Rxx or any Cxx, all the eigenvalues are, first of all, are real and they are non-negative. So this is the first theorem. So for a matrix, the pair of eigenvectors and eigenvalues are solution of this one. So this is a definition. So any matrix of any rectangular matrix, if for any Rx, if you solve this equation, you will find some solution for the pair of lambda I and Vi. So this pair is called the pair of this is eigenvalue, this is eigenvector, but they are associated together. So what we want to do, we want to prove that for any covariance matrix, these lambda i's are real numbers. Not only they are real numbers, but also they are positive. So this is the theorem. So it could be Rxx or it could be Cxx and so on. So the proof is coming from the definition, because I know that Rx is equal to mean of x Hermitian. So I use this one and I know these definitions. So I combine it to prove this property. So from this definition, which is here, and I could multiply both sides of this definition by Vi Hermitian. So what I get here, I get Vi Hermitian times Rx Vi. So this is equal to this one, and these times Vi Hermitian. So what I get here, I get lambda I times Vi Hermitian and Vi. So Vi Hermitian Vi becomes the Euclidean norm of Vi to the power 2. So obviously from here, I could get lambda I is equal to Vi Hermitian Rx and then Vi divided by Vi norm of this to the power, provided that this guy is not zero. Because this guy is non-negative and positive, numerator is real and non-negative, lambda I should be also real and non-negative. So it's kind of this one. So if Vi is not equal to 0, obviously. And if you put 0 here, both sides become 0, so this is an obvious solution. So we call the pair of eigenvalue or eigenvectors if Vi is not 0. So the Vi not 0 is a part of the definition of eigenvectors. So the proof is complete here. So numerator and denominators are both real and non-negative. So all the eigenvalues of any correlation or covariance matrix is real and non-negative. So there are lots of other properties that we could prove. We do only one of them. The rest of it is exercise for you. For instance, determinant of any correlation matrix is real and non-negative. So determinant is real and non-negative. The proof is easy because determinant of any rectangular matrix is equal to the product of these eigenvalues. All of these guys are non-negative, so therefore their product is also non-negative.